Empirical molecular formulas are a new topic that are going to be using percent composition that we learned last week. These are both two different kinds of formulas, and you're actually more familiar with the molecular formula as opposed to the empirical formula. There's not a significant difference between the two of them. These notes here are for page 17 in your flipbook if you choose to write them down. Now let's take a look at this today. First, the newer one, the empirical formula, is actually calculated from the percent composition that we learned last week, so we do have to have that information. All it is the lowest whole number ratio of the elements in a compound. It may not be the true formula, though. It is possible that this is just the smallest ratio available. It is also possible that it might be the real formula, but it requires another step to figure that out. The molecular formula is what you already know and what we learned in class. The molecular formula is the true and final formula of a compound. This is the real formula. So here are a few examples today. Empirical formula, for example, might be CO. But the real formula, molecular formula, might be C2O2, something that's multiplied greater than it. NH2 is a very, very simple formula. You can't divide it any lower, but a molecular formula of NH2 might be N2H4. A final empirical formula might be CH4. You can't divide this any lower, but there are many variations of CH4 in molecular formulas. For example, if I multiply it by 2, you might end up with C2H8. If you multiply CH4 by 3, you might end up with C3H12. All of these are molecular formulas that come from the original empirical formula. So some examples. Well, let's take a look at this one here. What is the empirical formula of a compound that is 25% nitrogen and 74.1% oxygen? First steps first, we need to assume a 100-gram sample. This makes it a lot easier for me. I could technically use any sample size, but I'm going to go with 100 grams because it makes my math a lot easier to work with. With that in mind, 25.9% of 100 grams means I have 25.9 grams of nitrogen. 74.1% is 74.1 grams of oxygen. I can't compare grams. Most of us know this by now. I can only compare moles. So I'm going to divide both of these grams by their molar masses. Nitrogen has a molar mass of 14.01 and oxygen has a molar mass of 16. This will get me the number of moles for each, 1.849 and 4.63. I need to have whole numbers though. In our formulas, we don't use anything but whole numbers. There's no half an atom, there's no 0.6 of an atom. It has to be a whole number. In order to get to that point, I'm going to divide them both by the lowest number of moles. So the 1.849 is the lowest number of moles present. I'll divide both by 1.849 and I end up with a ratio of 1 to around 2.5. That's a small problem. Again, I can't have half an atom. The 2.5 cannot be part of the formula. But if I double everything, I maintain the ratio and I also get whole numbers. So a ratio of 2 to around 2.5 means I still have a 1 to 2.5 ratio. That means I have 2 nitrogen and 5 oxygen. For the molecular formula, this is significantly easier. If you made it to this point, you can do percent composition, you can do empirical formula. The only thing we need left is a multiplier. Whatever the multiplier is what we're going to multiply the basic empirical formula by. To get this, though, we must know the real formula's mass. That usually means we need something like a mass spectrometer. In our problems, this is going to be given to you. So let's calculate the molecular formula of a compound CH4N. If we know the empirical formula is CH4N, and we know the molecular mass, the real mass is 60 grams. First things first, I need to find the molar mass of the empirical formula. I take all the carbons, all the hydrogens, and all the nitrogens, and I add it all up together. For this chemical, it's 30.06 grams. But we know the real chemical has a molar mass of 60 grams. So I'm going to divide the real mass by the empirical mass. 60 grams divided by about 30 grams. And that gets me a 2 as my multiplier. I multiply the empirical formula, the simplest one, by 2. I will end up with 2 carbons, 8 hydrogens, and 2 nitrogens as the molecular formula. You have 2 assignments this week. Both of them deal with empirical and molecular formula. I'm going to do with a couple of problems here today and solving 3 of the problems from the first assignment with you. And we'll take a look at problems number 1, number 4, and number 11, both of them being a fair example. First problem I'm going to work with y'all today is going to be number 1. Here we're given 88% copper and also 11.2% oxygen. I need to assume a 100-gram sample size because I'm given no other information. This is not a real sample, it's purely hypothetical, a theoretical question. 100 grams makes it easier for me because 88% of 100 grams is exactly 88 grams of copper. This also means that 11.2% oxygen means I have 11.2 grams of oxygen. I can't compare grams, I can only compare moles. I'm going to divide both by their respective molar masses. Copper has a molar mass of 63.55, and oxygen has a molar mass of around 16. When I divide these two, I'll end up with 1.38 moles of copper and 0.7 moles of oxygen. From here, I'm going to divide both by the lowest number of moles so that I have cleaner whole numbers. Lowest number of moles is 0.7. This results in 0.7 divided by 0.7 being the easiest of a ratio of 1. But 1.38 divided by 7 is close enough to 2 that it might as well be 2. We're going to have to round a little bit here because we do need whole numbers in our final answer. This means it's a 2-to-1 ratio of copper to oxygen. So I can write Cu2O1. But we know we normally don't write ones in chemistry, so I can finalize this as simply as being Cu2O as my final empirical formula. In the second problem we're going to work with today, question number 4, we're given 70% iron and 30% oxygen. I chose this problem because it has a little bit of an interesting twist to it. It does follow the same method as problem number 1. We're going to take a look at this one and see what happens. All right, so we're going to assume a 100-gram sample size once again. This makes it easier for me overall because here 7% of 100 grams means I have exactly 70 grams of iron present. That also means that 30% of 100 grams is 30 grams of oxygen present. I divide both by their atomic masses to find the number of moles present, 55.85 for iron and 16 for oxygen. This will tell me how many moles are present. With iron, I will end up with 1.25 moles of iron and only 1.875 moles of oxygen. I need whole number ratios. I will divide both by the lowest number here present, which is 1.25, and this will get me a ratio of 1 to 1.5, and that 1.5 is an issue. It's not something I can easily round up or round down. It's not like it's 1.1 or 1.9. I need to maintain a 1 to 1.5 ratio, which ultimately means it's a 2 to 3 ratio. This is why I chose this problem, and the final ratio of iron to oxygen is 2 to 3. So when I write this problem out, we will end up having Fe2 2O3 as our final answer. Be careful whenever you have any ratio close to 1.5. And the third and final problem I want to work with you guys today, this is going to be a molecular formula problem. Here you will need to know the empirical formula first, as well as a molar mass to solve for it. In problem 11, both of them are given to us. The empirical formula for problem 11 happens to be CH3O, and the molar mass is 62 grams per mole. With these two pieces of information, I can solve for the true and final formula. Here, I need to do the molecular mass over the empirical mass to find a multiplier. This multiplier is what I'm going to multiply the first formula by. I do know my molecular mass of being 62. I do not know the empirical mass right now, but that's pretty easy to solve for. Because I already have the empirical formula of CH3O, I simply solve for its molar mass. 1 carbon is present, 3 hydrogen are present, and 1 oxygen is given. Multiply each by their atomic masses, carbon being 12, hydrogen 1, oxygen being 16. Once you add up all this together, you'll end up with the final molar mass. We have 12 plus 3 plus 16 total, which results in a total molar mass of 30 1. This is the mass of the basic formula, not the real formula. But now that I know the empirical mass, I can go ahead and plug it into my formula. So I'll remove my unknown variable and plug in the empirical mass of 31. 62 divided by 31, molar mass divided by empirical mass is 2. My multiplier is 2. All I need to do now is multiply the first formula by 2. So that is 2 times the carbons, C2, 2 times the hydrogens, H6, and 2 times the oxygens, O2. And that will be the final formula.